Yeah, so I put this as a title, but maybe I will tell you about one other experiment that we've done in Cambridge as well, because I think maybe it's interesting to tell you about something else, and I think there should be time. So let's see how it goes. So just to give a brief outline of the talk, I'll give some introduction of why we were thinking about, how we came to be thinking about these experiments, why we think they're interesting, and in this section maybe I tell you about this other piece of work that we've done, and then the main part of the talk is going to be about this Brillouin light scattering in yttrium iron garnet spheres, and I'll show you the experiments that we've done and maybe some thoughts on how we can improve these experiments and get to some more interesting physical regimes in the future. Okay, so as a background on this, so I just wanted to, maybe one way to think about these experiments, or this general area of strong coupling in magnetic systems with electromagnetic fields, which is, I guess, the title of this workshop, then what does this look like? So one way to think about this is that often optics or microwave electromagnetic fields in general are often used as probes of magnetic properties or dynamics in some experiment that we do in spintronics or magnetism. Or conversely, it's somehow used as a pump for some system. So we might have some strong, intense laser pulse that's got some known form, and that electromagnetic field is fixed with some large amplitude and is inducing some change in some physical property. Or we're looking at using some electromagnetic field as a probe, where we're just looking at some small change in the electromagnetic field due to some property of the material that is not affected by the optical field. And it's interesting to think about whether there's some other situation in which the modification of the electromagnetic field and by the material and by the magnetic material, and the way in which the electromagnetic field modifies the properties of the magnetic material are sort of on an equal footing, and therefore we have to consider the dynamics of both the electromagnetic field and the magnetization on an equal footing, and whether there's some interesting physics that happens there. And so I'm going to briefly go through what this, maybe in terms of probes of magnetic properties and dynamics, two examples of where we use electromagnetic fields to probe properties of magnetic materials is ferromagnetic resonance and Brillouin light scattering. And I want to just talk briefly about these two aspects and whether we can take both of these things into a different regime in which the electromagnetic field is more strongly interacting with the magnetization dynamics. And Hans afterwards is going to tell you more about this on the microwave side, and this on the optical side. So just to go through the ferromagnetic resonance side. So you all know this, but maybe it's interesting to look at some sort of traditional ferromagnetic resonance experiment where maybe more often people now use broadband coplanar waveguide or something like this. But in the traditional case, maybe you have some microwave cavity, and what you do is you put your microwave source and you measure how much power you get reflected at the resonant frequency of this cavity. And what you might do then is just tune the magnetic field and measure this reflected power on resonance with the cavity. And because this magnetic material is just perturbing the cavity and introducing some dissipation when the magnetic field makes that ferromagnetic resonance frequency resonant with the cavity frequency, then we get some small change in the reflected power, which we can use to tell what the resonance frequency field of that magnetic material is at that cavity frequency. But what Hans has shown relatively recently, and what he'll tell you about later, is that if you make that the interaction between the cavity and the or it is possible to get into a regime where both the magnetization dynamics couple in such a strong way to the microwave cavity that we don't just have some fixed cavity resonance that we're perturbing, but really that these the ferromagnetic resonance frequency and the microwave cavity frequency strongly couple in so that these modes become a hybridization of both the cavity field and the ferromagnetic resonance field. And this has been picked up by a lot of groups, and I just show this paper from Professor Nakamura in Tokyo, where they show similar splitting, and now they've done gone much further with this in using this to couple to some superconducting qubits and do spectroscopy of the number of magnons in this yttrium ion garnet sphere via this strong coupling to the cavity mode. And one important parameter in ascertaining this coupling between the microwave field and the ferromagnetic resonance field is this what's called the cooperativity of the system. And this is just this expression here. So what we got in it, we've got the coupling rate, which is telling us about this splitting between the two modes, and the two dissipation rates so the line width of the microwave cavity mode and the line width of the ferromagnetic resonance mode. And obviously this would be normally the Gilbert damping, which is frequency dependent, but if we just imagine that it's some fixed line width in frequency, then we can write down this single photon cooperativity, and that tells us about how well we can resolve these two peaks. And so if we had a cooperativity of 1, we would just about be able to see that we had this splitting between these two modes. And this is what defines this strong coupling regime, is that if we have a cooperativity greater than 1. And this will be important in the optical experiments as well, in looking to get to the similar regime of this as cooperativity of about 200 or something. And we're interested, we will be interested in whether we can get to that in the optical field with the optical field as well. So I just wanted to show you briefly one experiment that we've done on the microwave side in Cambridge. My colleague Nick Lambert, who's a postdoc of Andrew Ferguson. And what we did is, so in these experiments we've got this single Higgs sphere in the cavity, in the microwave cavity. But you can do some other things, and the first most obvious thing is to put 2 of these spheres in the cavity. And then what we've done here is, so here's our microwave cavity. It's just a piece of coax where we've got some coupling capacitors at each end, so this length defines the resonant frequency of the microwave cavity, and we've put these Higgs spheres at the antinode in the magnetic field of the second harmonic of the microwave cavity. And we've put these little coils on here so we can locally tune the magnetic field, or tune the magnetic resonance frequency of the sphere. And well, the obvious thing you can do, so here we've got the microwave cavity, and we can tune. So what we've done here is detune the spheres from each other and just tune them through the microwave cavity. And you can see that they strongly couple, but it's a bit of a mess. And the dynamics are actually quite complicated here, because we've got 3 things. We've got 2 Higgs spheres, and we've got the microwave cavity as well. What's more interesting is to think about moving away from the cavity frequency, and then it turns out that the microwave cavity still affects the dynamics in a way that we can more easily understand, and to do with the way that the dispersive properties of the microwave cavity. So what we're going to do, we're not going to look here, we're going to look at some detuned values. So we're going to detune both spheres from the cavity and look whether they couple to each other via this microwave cavity, even though we're detuned from it. And this is something that people have exploited with superconducting qubits in putting them both in a similar microwave cavity and looking at how they couple, and that's a useful tool for Hans, were you going to ask a question?
Yeah.
Yeah.
But I just don't want to break this up. The dispersive regime, are you addressing this with the microwave tones, or?
Yeah, so I wasn't going to go into the details of the two measurements because I think, but yes, essentially we pump the, so we have a drive tone on the at the ferromagnetic resonance frequency, and we watch the microwave cavity in this because effectively because we reduce the magnetization, we get a shift in the cavity frequency that we can probe with a separate microwave tone. Yeah, but for the purposes of this, it's just a different measurement of the same thing, and it's quite nice because it's just sensitive to MZ, not some complicated dynamics of the cavity. So we throw away all information about the phase, so it's easier to understand what's going on. So what you can do with this this geometry is quite nice. You can short out this capacitor here and turn it back into a piece of coax, and that's nice because then you can just do FMR of these two Higgs spheres in the cable, and what you can do there is tune them through each other and see that they just cross because they don't talk to each other. This distance here is about 3 or 4 centimeters, so there's basically no dipolar interaction between these two spheres. What happens if we introduce the cavity again? Well, here we can clearly see that they're talking to each other now. So we've got these two Higgs spheres, and now they're coupled to each other. So we've got two modes, whether they're in phase or out of phase, the precession in the two spheres. So this is really nice because even though these are separated by some quite large distance, we're coherently coupling these magnetic moments in some passive way just by modifying the local electromagnetic density of states and making this one-dimensional channel, which is not talking to each other by emitting photons into this waveguide and absorbing them, but just through the off-resonant properties of this cavity. And in the superconducting qubit experiment, they would talk about this in terms of virtual photons talking to each other through the...
the same thing, the virtual photons simply means the same. I'm a bit confused about the terminology. Isn't that the same thing? If you say they're virtual transitions,
yeah.
Isn't that the same as saying what you're saying here?
Yeah, yes, exactly. I mean, what I'm saying that it's basically the off-resonant properties of the cavity. It's just like a near-field effect of the...
So can I interpret this as a virtual emission of photon by the magnetic system into the cavity, and then this virtual photon is absorbed by the other one?
Yes.
Okay.
Yeah.
How do I understand this, that the lower branch has much higher intensities than the upper branch?
Okay, so that's interesting. So you can read about it in our paper, but basically it's because, so your our drive comes in here, and there's a node in the field here, and depending on what the frequency is, we've got the same field here as here, or the opposite field here or here.
So one of them sitting in a node, the other in node.
Yeah, and so depending on the relative phase of the two, because these have opposite phase, these two modes, we drive one of them and not the other one. And actually, as you tune the total magnetic field, then you can see that this changes this symmetry. And then what you can do, so I won't go through the theory, but so this looks like some XY coupling like this, and we can it depends on the detuning from the cavity mode, and you can map that out. So we measure this splitting, which tells us what this coupling here is, and we can find that it follows the expected dependence as a function of frequency. This is where the two first harmonic and second harmonic of the microwave cavity are, and so we have to take into account all these different cavity modes, but we can understand why this coupling. So that's something. So it's nice. So we can spatially separate magnetic moments can be passively coupled over quite a long distance via this electromagnetic cavity. So that's the microwave side. What about optics? Is there something that we can do in a similar spirit? Oh, sorry, yeah.
So this coupling between two spheres, this coupling strength, but it should depend on this distance between two spheres.
So it depends on the detuning from the cavity frequency. So obviously, if you tune, so this length here defines what the cavity frequency is, assuming the impedance or the phase propagation length is the same. So if we make the thing longer, then we're going to change the positions of the cavity frequency. So it's quite complicated the way in which you cannot make it really long and then.
Does it decay exponentially, this strength, or is it more or less constant?
So there's several parameters that will affect. So.
I think what Stefan says is keep the length of the cavity the same, but move your magnet from...
Okay.
Yeah,
okay. So if we move them about here, then, so if we imagine, let's look at the second harmonic of this cavity, so it's going to have some field profile that looks like this. So as we move these about, we're going to change the coupling to that particular mode. The coupling to some other modes will be increased depending on where it is with respect to the antinodes in this field in the cavity. But it's not a trivial dependence on position, because it depends which mode you're coupling to, so wherever you're close to. So if we were close to the third harmonic, then maybe it would be better to have them spaced in a different position. But does that make sense?
Damping in the cavity is negligible, basically. The damping in the cavity is negligible.
Yeah, right. So this is the important point, because we're...
It's finite, but it goes over a meter length scale. So on these distances, you can forget about damping of the cavity.
And this is about this. So because it's effectively virtual photons, then there's no dissipation in the cavity. So, or negligible dissipation in some approximation. Does that make sense? Okay, so that's the microwave side. What about optics? Is there some similar experiment that we can do on the optical sides, coupling some optical electromagnetic field to some magnetization dynamics, and do some interesting experiments there as well? And we can go back to some quite common experimental tool that's used in spintronics and magnetism, which is Brillouin light scattering, where we're using the optics as a probe of the magnetization dynamics. And can we take that and make it stronger by introducing some optical cavity? And as you see from the previous experiments, it's quite common in the microwave side to use these yttrium ion garnet spheres, because they have very low damping, because the two magnon scattering is very small, because they're highly polished and there's no irregularities on the surface. And but what we've got effectively is a highly polished sphere. It's transparent in the infrared, and so this is a natural thing to think about, whether this can be an optical cavity. So we've got this built-in optical cavity. We've got some quite strong magneto-optical coupling. This material is used in optical isolators and things like this, where you need some Faraday rotation. And because this is quite an obvious idea, about the same time these three groups started looking at this whispering gallery modes in these, which I'll show you in a minute, in these Yig spheres. And I'll tell you about our results, but also Professor Nakamura in University of Tokyo and Hong Tang in Yale, also looking at this similar system. So what does our experiment look like? So we've got our yttrium ion garnet sphere, and what we're going to be looking at these optical whispering gallery modes that propagate around the equator of the sphere, and basically this is just confined by total internal reflection at the surface, because we've got some high refractive index here and some n=1 outside, and this is going to confine this optical mode, and we're going to probe that by putting this coupling prism basically in contact with this sphere, and then we get some evanescent coupling to the sphere from our probe beam which we focus to some small spot on the inside of this prism. And what do we measure when we do that? So what we're going to do is we're going to, just to start with, put a photodiode over here and measure how much power we measure as we tune the optical wavelength. And what we see there is these nice Fabry-Perot modes in the sphere. And as we change the sphere diameter, then we change the free spectral range of these modes, and in a way which depends just on the circumference. And so what we're doing is just changing the azimuthal mode index of these whispering gallery modes, so just the number of wavelengths that we can fit in around the circumference of that equator, that sphere. And so you can see these have quite nicely resolved modes, and they have a Q of about 10 to the 5, depending on the diameter. Can we identify something more about these optical modes? So usually, these optical whispering gallery modes are defined by this azimuthal mode index, which is the number of wavelengths in this direction. We can also think about the radial mode index, which will tell us about how many nodes in the radial direction. So this is just the lowest order one, because we only have one antinode in the field, and also there will be an azimuthal mode index in the polar direction as well. But we can actually identify which modes we're driving. So you'll notice here that we've always got this second set of modes here, and we can identify it by looking at basically at the dispersion over some wide. So these are the resonant frequencies, the free spectral range, and the difference in this separation here that we measure over some wide frequency range, and that allows us to identify this second peak as this second radial mode of the whispering gallery modes. So it's nice because it's not so important for the experiment, but it shows that we can really identify what these whispering gallery modes are and be confident that what the optical modes that we're looking at are. One thing that's going to be really important is that because of the boundary conditions, of the electromagnetic field at this interface with the surface of the sphere, there's quite some strong geometrical birefringence in the what that means is that we get a different, slightly different refractive index for horizontally polarized and vertically polarized modes in this sphere. So we're going to get two mode families, one for vertically polarized field and a separate one for horizontally polarized field. And that's going to be important because, as you know, if you do some Brillouin light scattering experiment, what you do is you put in one polarization and you measure with the orthogonal polarization. And so if we want to look at Brillouin light scattering, we're going to be talking about scattering from one polarization to some other polarization. And what's nice is, because we've got this splitting between them, these modes, what we're going to do is tune the ferromagnetic resonant frequency so it's resonant with this splitting between these two modes. Just to summarize that optical mode identified, they can be identified, and we've got some of this horizontal vertical polarization splitting, which can be comparable to the FMR frequency for one particular sphere diameter. So next we're going to try and do some Brillouin light scattering experiments in this system. So here, as well as our pump with one polarization, we're going to measure with some spectral resolution using this Fabry-Perot echelon, what we measure in the orthogonal polarization. And what's nice is actually this coupling prism is slightly birefringent, or quite strongly birefringent, so this opposite polarization comes out at a different angle. And at the same time, we're just going to drive ferromagnetic resonance in our sphere by applying some static magnetic field and then driving it with some microwave field. And so we can do two experiments. We can do with opposite input polarization and measure for the two orthogonal output polarizations, what we measure. And you can see here that we see quite strongly this anti-Stokes and Stokes emission, which is separated from the input laser wavelength by the FMR frequency. So we're seeing this Brillouin light scattering, but what's interesting is we're getting this strong asymmetry between Stokes and anti-Stokes depending on what the input polarization is. So next what we can do is we can just extract how strong this peak is. Tells us about what the efficiency of the Brillouin light scattering process is.
Sorry,
Yeah.
what's the peak on the Stokes side? The one on the Stokes
This
side
one
is a
here.
different frequency. Yeah.
This one here is just the, because it's a Fabry-Perot, we just get repeated.
It's because of one pair of one pair of photons.
Oh, okay. So this is just the orthogonal effect. So
Yeah.
I will ask you, how do you know that this omega FMI is from the that this is anti-Stokes but not Stokes from another side?
Because basically just because of this this frequency here, because we know what frequency.
You know what you're saying.
Yeah, we're driving, so we know what this frequency is.
Excuse me.
Yeah.
You did mention that the ratio between Stokes and anti-Stokes depends on what polarization that you use. I didn't understand the point. Why?
I think this will become more clear as we continue. Just as an observation that we see for one input polarization, we only see one, and for the other, we only see the other. Okay, so we're going to just measure the height of these peaks as we tune now. So this is just the Fabry-Perot measurement, tuning the frequency. We can also tune the input laser frequency, and what we can see is then measure the efficiency of the Brillouin light scattering process as we tune that laser input frequency. And so this is clear to look at this. So here are whispering gallery modes. It's not so clear for this input polarization because the coupling is harder to get right, but you can see these whispering gallery modes here. And what you can see is we get a peak in the Brillouin light scattering efficiency when we hit that optical whispering gallery mode. So now we've got, so this is tuning the input laser wavelength. There's a second parameter that we can tune, which is the ferromagnetic resonant frequency, which we can tune by changing the static field. And so this is the graph of this, so that here we've got the ferromagnetic resonant frequency plotted here, and this is the input laser wavelength for the two horizontal and vertical input polarizations. And for reference, I've put, this is just this spectroscopy in transmission of what the whispering gallery mode, so we can see where they are relative to what our input laser wavelength is. And so let's just look at the horizontal input polarization, and we can see two peaks basically in the Brillouin light scattering efficiency. One that shifts as we change the FMR frequency, and one that is static when we shift the FMR frequency. And we can understand that by thinking about the resonant enhancement of the Brillouin light scattering process of the input and the output optical field. So here what's happening is we're putting in an optical photon, and we're getting one out at this vertically polarized whispering gallery mode. So depending on what the FMR frequency is, this peak shifts, because at that, depending on the frequency, if we want to hit this vertically polarized whispering gallery mode, we have to shift longer in wavelength in order to scatter into that mode. Whereas this peak here is resonant enhancement of the input optical field, and that means that doesn't shift with FMR frequency, because this peak doesn't shift with FMR frequency. What's nice is we can tune it to this point here, where we're both enhancing the input optical field and the output optical field. So this is what was called the triple resonance condition, because we are resonantly scattering from this mode to this mode, rather than just enhancing one of either the input or output optical field. We can do the same experiment for the opposite input polarization, and here we got the opposite dependence, because here we're scattering either into this horizontally polarized mode, where we have to detune the depends on the FMR frequency, or which is enhancing the input optical field of the opposite polarization. And so this data here I've normalized to the peak at each FMR frequency, just so we can see clearly these modes. But we can also plot, so if we plot the peak efficiency at each FMR frequency, we can see this broad resonance in the Brillouin light scattering intensity that follows the expected dependence on the FMR frequency from some calculations that my colleague Andreas Nordenkamp has done. And what you can see is that we're tuning this FMR frequency, but the line width is given by the optical modes. So even though these whispering gallery modes look quite sharp, the bandwidth of this is about 1 gigahertz. And so that's defining this resonant peak in the Brillouin light scattering intensity. So even though we're tuning a microwave frequency, our line width is given by the optical frequencies. And that's why this is quite broad, and we're not getting some sharp enhancement of the Brillouin light scattering efficiency at this triple resonance condition. One thing that's kind of interesting about this is that it turns out just from how large that horizontal-vertical polarization splitting is, that the two modes that we're looking at here have different azimuthal mode index. So that means different number of wavelengths going around the whispering gallery mode. And that's kind of interesting, because another observation, separate observation you might make, is that we're driving the Kittel mode of the of this sphere, so it's a uniform mode at k equals 0. And usually you wouldn't imagine that you can measure Brillouin light scattering from some k equals 0 mode. But actually, if we think about what it looks like for some optical photon traveling around this this sphere, the direction of the dynamic component of the magnetization is changing depending on what position I am around the sphere. So although this is a k equals 0 magnetic mode, the optical interaction that the photon sees is actually at some finite wavelength. And so we get from this dependence, we get some phase factor that depends on the position, and that's compensated for by our change in one of the azimuthal mode index of the whispering gallery mode. So in summary, I guess I'm running out of time, so we can enhance the Brillouin light scattering using some optical whispering gallery modes, and we can reach this triple resonance condition. And one thing that we're interested in, that maybe I didn't talk about, is that is this other community, not spintronics people, but opto-mechanics people who are interested in the interaction of optical fields with some collective mode of some mechanical resonator. And one of the analogies that the people working in this field has been making is that, can we do similar physics with the collective mode of the spin system, that is the magnetization dynamics. So we're interested in whether we can do similar experiments to opto-mechanics in this system. Just quickly, we did the cooperativity for the microwave system. What does our cooperativity look like for this optical system that we've been measuring? And it turns out not very good. So at the moment we're down about 10 to the minus 15 for the single photon cooperativity. It's actually a bit different in this optical case because it's a parametric interaction. We can actually enhance it a bit by having the pump optical field. But we're still a long way from, these are some opto-mechanics experiments, and so it's nice to compare what single photon cooperativity they have, and we're obviously a long way from being able to do comparable experiments. So can we enhance it a little bit? I could just go quickly through this, but basically most of the parameters are fixed by the material. So the optical dissipation rate is basically absorption, residual absorption in the Higgs band gap. The magnetic dissipation, these things have been optimized because people care about building RF filters and things like this, so we're not really going to be able to improve this by some significant amount. I mean, these Yig spheres are designed for these RF filters, so they are optimized by some industry, right, since the 1960s, so I don't think we're going to be able to improve this very much. What about the coupling rate? So this we can do something about. So if you imagine that we've got this large 1 millimeter sphere, it's got some enormous mode volume. We can imagine, so, and if you do the calculation, you can get what this coupling rate is. So at the moment we have about 1 hertz, and it depends on the, well, 1 over the square root of the number of spins. So if we can reduce this number significantly, then we could increase the coupling rate significantly. And at the moment this is enormous because we've got this 1 millimeter sphere. So what's the smallest cavity that you can imagine making? Well, it's going to be of the order of the wavelength of the, or half the wavelength of the optical field. And so we could, in principle, get a 10 to the 5 increase in the coupling constant. Maybe we can decrease the line width a little bit because we've not optimized the coupling. But if we add up all these things that we can, in principle, optimize, then it's quite possible that we could get to not cooperativity 1, but cooperativity or single photon cooperativity 10 to the minus 4 or something. And that's okay because we've got this parametric interaction. We can just turn on some optical pump, and in principle it seems possible that we could get to some cooperativity where close or greater than 1. And that would be really interesting because then we've not got just the strong coupling on the microwave side, but also on the optical side as well. Okay, and then I'll finish there, and maybe I can answer some questions.